Thank you, everybody, for joining. Today, we are talking about plastic hot plate welding made easy. My name is Jason Dornbos. I am sales manager at Extol, and with me today is...
I'm Catherine Urives. I am the inside sales engineer at Extol.
Here's a quick agenda for the topics that we want to talk about, and of course, you can add to this as you ask your questions. We're going to cover what is hot plate welding, the very basics, how does it work, what are the benefits of the technology, and then where is it used? So some example applications. Then we'll talk about how you can design your parts so that you can use hot plate welding as a process. And then we can talk about what the equipment looks like. What does a hot plate welder look like? But first, I have a question for you. Why did you sign up for this webinar? Is there something specific that you're hoping to learn? Are you just trying to up your knowledge about plastic welding? Is there a hot plate welding project on the horizon and you're hoping to understand the process a little bit better since you're going to have to use it? Let us know why you signed up for this webinar. Drop your comments there in the chat. I signed up for this webinar because I'm supposed to present.
Me too. That's crazy.
And I have some experience in hot plate welding. We have a lab here at Extol, and in the lab, we take customers' applications and we test them out and we try things and we'll do prototypes and all that kind of stuff. And I spent a fair amount of time in the lab doing hot plate weld prototype work with customers. So I learned a lot about hot plate welding simply from using it and being very, very hands-on with it. Thank you for your comment here. It is for gaining knowledge for this process. Great. Well, hopefully we can fulfill that. New to the company, welding process with fiberglass. Yep, we can do that. We'll get into what materials and the fillers, how they impact the process. Anybody else? I'm gonna go forward.
Well, for anyone who is a little bit new here, before we get to the meat of the presentation, we just wanted to give a little rundown of who Extol is. We are a locally owned company operating out of Zeeland, Michigan, and our mission statement and goal in partnering with you is to solve your complex manufacturing challenges. This is actually a philosophy that we depict in our logo. So we find that often in the industry, you have companies with plastic welding expertise, and then you've got companies with custom automation expertise. Now, companies with that plastic knowledge are really deep technically. They know what it takes to join plastic. However, they don't necessarily do overly well with custom solutions. Your part has to fit in their box, and if it doesn't, that's a you problem. You better change it, not a let's partner together and figure out a way to make it work. Meanwhile, custom automation companies or machine builders have such a wealth of knowledge of equipment and its capacity, but they don't necessarily always have the deep technical knowledge needed to have a successful joining application. So where Extol comes in is we try and be the best of both worlds. We want to help you get a configurable plastic welding solution that is optimized for performance for your specific application. This means the equipment suits what you need it to do, not what we want it to do. And we partner with you to develop a specific process that is specific to your application and achieving the needs that you have. We like to partner with you in kind of 3 different areas: engineering services, the actual assembly technology, and then the automation or using the technology itself. So engineering services, this looks like Jason mentioned, our applications lab partnering with you and helping you design your part, looking at it when it's still in CAD, providing recommendations, both for the design and for the technology you should use. You don't have to be the one who's speccing out laser welding. You can just say, I have to put these parts together. How? And then they will give you recommendations of, this is what you need to do for laser, this is what you need to do for hot plate, and then the advantages of one or the other. Then from that point, after the design is ready to go, we can help you prototype the assembly. That way you don't have to commit to a piece of equipment. You can actually try out the part. You can put it in your larger assembly, test it, validate it, stuff like that, with functional prototypes that we can build in-house so that you know without a doubt that the process is meeting your needs before you end up with a machine that potentially doesn't hit the targets you need it to. And then along with that prototyping, we can help with validation. We can burst test, leak test, tensile, throw it at the wall, stomp on it a couple times. Pretty much anything we need to do to validate that the technology that's chosen meets your needs. Then in the middle here, we've got plastic assembly technologies. These are technologies that we offer equipment for or integration packages for. Not every joining technology is pictured here, but we are always willing to integrate stuff into equipment as well, even if we are not the masters of it. So just some examples of joining technologies in the middle there. And then on the right side of the screen, you'll see we are a custom automation house. So we can provide you with a fully automated solution, where there's one operator that only touches the parts when they load and unload the nest, or all the way down to an integration package where we just simply give you the technology and then you integrate it into the machine. I feel like something that we do really well as a company is because we have that custom automation expertise in-house, we understand what is needed to make that equipment effective and simple to plug into your specific machine for success. So we've got quite a variety of ways that we can offer the technology for you, and we want to be an information center and an easy button. So if you've got questions, we're here to help. On that note, I know that you're all here for hot plate welding. So another little question for you. How much experience do you have with hot plate welding? I saw some messages coming in about just learning, new to the company. Is there anyone who feels pretty good about their hot plate welding experience? Anyone like a 5?
We got some 1s and we got some 2s. 1s, 2s. Anybody can anybody beat a 2?
Good question.
2 is the best.
If anyone's a 10, we're happy to unmute you. You can present with us. I think it'd be fun.
We got a 7. Nice.
Oscar, I'm curious about what your background is. Have you seen hot plate welding before? Have you had a project that's used it? Curious where that 7's coming from.
Let's get into some of the basics. So this is plastic welding. Hot plate welding is a type of plastic welding process. So if you take a step back and look at all different types of plastic welding, you need 2 things. You need heat. You have to get heat into the material, and then you have to apply pressure somehow to these 2 materials so that those warmed up or melted materials can bond together. So you need heat and pressure, and that's all plastic welding. And hot plate welding applies the heat in a certain way and applies the pressure in a certain way. So what exactly is hot plate welding? Well, the graphic on the left points out a couple of things. First, it's a contact joining method. So that means the plastic materials touch a heated tool. They actually physically touch. There's a heated tooling plate. So that tool is brought up to a controlled temperature. There's heaters inside of it. There's temperature probes inside of it so that it's closed loop, and you can control the process around the amount of heat is on the tool plate itself. And then it's using conduction heat transfer. So because the plastic is touching the hot tool, that heat from the tool conducts into the plastic parts. And lastly, it produces strong leak-proof welds. So that's the graphic on the right. A couple of people asked whether or not you can actually get a hermetic seal from hot plate welding. Yes, you can. And it's often used in applications where a hermetic seal is critical for the part that's being welded. So here's a quick video showing the process. This is just a little sample part. What you'll see is you load parts in 2 separate tools, and then they're brought, like I said before, into contact with the heated tool, and then they're brought together and forces applied to get them to weld. That's a very, very fast process, and there's a couple reasons for that in this app. Not all hot plate welding is quite as fast. It all depends on the size of the part, the materials, several factors. So here are the steps of the hot plate process. First, you saw the components being loaded into tooling. That tooling is designed to support the weld ribs. The surfaces where we're actually going to be welding, you know, if this was just a bottle or a small part that had a rib along the perimeter, there might be just weld ribs along the outer edges. Sometimes there's weld ribs on the inside components of the parts. The press tooling needs to support the part as close to those weld surfaces as possible so that they don't bend or deflect out of the way when force is applied. Next, those parts are brought into contact with a heated platen. So one of the questions that was asked during registration was about part warp and how that impacts the process. So first, the tooling is designed to try to hold the parts very, very tightly so that they can partly take out some of the warp that might be present from molding. But the other thing that's really a benefit of the hot plate process is now we're melting the plastic surfaces on a machined heated tool. And that heated tool is very precisely machined so that we're going to melt away any of the molding irregularities that might be on your weld surface. So if you have high and low spots, areas where there's material sink, we're melting the plastic onto the heated tool and we're eliminating all of those inconsistencies on the top of your part. After melting and you've got enough heat into the plastic, the materials come off of the heated tool, it gets out of the way. This is called the open phase. And then they're brought into contact with each other and a force is applied to get them to seal. Here again, the tooling is very critical. We have to support the weld surfaces because we want to make sure that all of the force that we are applying from the machine gets into the parts and not into anything else. The tools don't have hard stops when we're using a servo-driven hot plate welder. So that means we know all of the force that machine is applying is going into the parts and not anywhere else. And then lastly, once the parts are welded, press opens up and you can take your welded component out. So there's several different parameters that you can use to affect how much heat and how much pressure you're applying, and you balance those two things to get a good weld. So on the melt side, we can control the temperature of the heat plate. Typical melting temperature or heat temperatures are 450 degrees on the very low end, I would say, and then upwards of 900 degrees Fahrenheit. So you can get very, very hot tools. You can get tools that are still very hot. You're going to burn yourself, but much cooler relatively. Obviously, the hotter your heated tool, the less amount of time it takes to get that heat into the plastic. For polypropylene, what are the temperatures? Polypropylene is one of the most flexible materials as far as what temperature you can use. You can weld it at what we call a lower temp or a higher temp. Mm-hmm. I think pretty commonly we like to use a hotter temp just so the process is faster. Mm-hmm. But some customers prefer the lower temp. They think that it maybe will provide stronger results long term. Mm-hmm. But so pretty average temperature would be like a 500 degrees Fahrenheit would be the lower temp, and then upper temperatures maybe 850 degrees Fahrenheit for polypropylene. Question about any information about the dimensional. Can you expound on that question a little bit? I'm not sure what you're asking there. The other parameters that we can affect are the depth. So when we contact the heated tool, how much further beyond initial contact do we displace material? The deeper you press, the more area that you're going to melt, and the deeper your heat gets into your part. That can also affect the stack height of your part and all that. Do the tools stay hot all the time? Yes, they do. Mm-hmm. Yep. Because we're talking about a big, massive heated tool, and it takes a little bit of time to ramp up to the temperature, mm-hmm. and we just maintain it at that temperature throughout a shift. And then maybe if you're not going to run it all day, you can turn it off, and then we can get into the equipment afterwards, but you can have an automatic startup so it's hot and ready to go at the beginning of your manufacturing shift. The tolerances that can be achieved is very tight. Mm-hmm. If we're talking about servo-driven hot plate welding. Trying to remember what the actual number.
About 5 thou on either side.
Okay. Yep. 5 thou stack height tolerances. beyond that, you start to really get into how tightly can you hold the parts with your tool, and how tight of tolerances can the plastic parts maintain.
Typically, the plastic is the one that can't do as tight of tolerances as the equipment is capable of.
Which is one of the reasons why hot plate welding is used, because if we have all these, variation in the overall molded height of your two parts, we can melt it and then bring it together and make the height actually more consistent than what it was to begin with. The last parameter would be time. So when we are melting the parts on the heated tooling, we can melt it for a long time. We can melt it for a short time. The longer you sit there, the more heat you get into it.
There's a question about, is there a set amount of warpage in the part that is acceptable? It's a little bit of a tricky question.
Yeah. It kind of depends on how big your parts are. If it's a big part and it's so sort of flexible and to a degree, like a lot of that we can take that warp out with tooling. But if it's a really small part and it's really, really warped, it's going to be harder to do that.
Yeah. To get your tool action to actually even retain the part, not necessarily the process even. The
machines are able to apply a lot of force. And sometimes what we do, if there's a part that's very warped, is we use the press to drive those parts into the heated tool or into the press tooling. So we can bring them together before we've melted anything, push hard so that those parts are fully seated into the tooling, and then we fire clamps to hold them there. Then we pull it apart and then start the welding process. I don't know that I can give you an exact number, but I would say hot plate welding is able to accommodate fairly significant amounts of warp. As long as there's enough room, there's enough melt rib to work with to melt away. Yeah,
I think that's a critical piece. Is you might be able to get it through the process, but depending on the stress you're pushing into the part by trying to flatten it, you might get a spot that sits really low, another part that sits a little bit high. And then after you take the part out of the nest, what stresses are being acted on the part from trying to flatten it? So a bit of a gray answer, but we can test it. We can prototype your parts and see if the whatever warp you're getting of the part out of the mold is acceptable or
not. Common materials. We'll talk about materials in a minute. The Victor asked, can the two plastic parts be welded right after the injection process? Yes, it will impact the process parameters that you use, knowing that your parts are starting out warm. But yes, you can weld directly out of the injection mold machine. So 3 parameters for the seal and weld phase. The depth, so how deep, once the melted parts now are touching each other, how far beyond that? That's your weld depth. How much do you push on those parts? The more you push, the more material you're going to squeeze out of your joint, but you also need to push so that you get force, and that's the second parameter. The amount of force that you're applying to those molten surfaces is important for good strength. You're trying to create new molecular bonds, and force helps get those bonds made. And then lastly, time. How long do you hold those parts under a pressure to get a good weld? And that's all stuff that we can control.
Got some questions about part size, which I think we're going to get to in a little bit. But there's a question about the bead of flash that's created. How do we deal with that? Do we design for it? Do we remove it after?
Yes. So most applications, if the flash is something that you don't want to see, so if there's an aesthetic concern with the flash, there's a couple solutions. One is in your part design, you design a wall or some kind of a flash trap to hide it behind some kind of a skirt or something like that. And that's, I would say, probably the most common way that people deal with that. You can trim the flash after welding. If you're welding something like a ball or something like that for sports, and like a ring of flash around the ball would impact the way it performs, then yes, that would be an area where you'd want to trim it off. Flash from hot plate welding it's not like vibration welding or other vibratory or friction processes. It's not going to dirty anything. It's contained and it sticks to the part. So it's not like it's going to fall off or break off or anything like that.
One thing is too that I get asked a lot is if the flash is contributing to strength at all. Which if it is, it's a very negligible amount. Really, the strength is coming from that chemical bond from the weld joint itself, not that displaced material.
Exactly. Are both sides of the hot plate temperature the same? Depends. It depends on the machine. Some machines, yes, and some machines, no. So we've built machines that have different tooling plates, and there's an isolator between the two, and then you control the temperatures independently. In other machines, we have a single plane of heated cartridges that heat the whole tool together. So then you would control the amount of heat you're getting into your parts by maybe reducing the amount of melt time on one side versus the other. So there's different ways to control how much heat you're getting into the part. And then, you can have different temperatures of the heated tooling, or you can have them both the same.
Looks like a question about a screen membrane attached to a plastic part. Have we ever explored this type of application?
Film sealing.
Yep.
Yes, we have done that kind of thing, and that might be a topic for a future webinar. I know we're actually working on a blog post about film sealing as well. So
stay tuned.
Stay tuned.
And then if prototyping injection molded part, can you guys test the weld before having the actual injection mold part?
We sure can. Right?
Yeah.
Yeah. All right.
Benefits of hot plate welding. We touched on them a little bit. The biggest ones, though, are a hermetic seal can be achieved. A strong, robust weld can also be achieved with this process. With the proper joint design, you can achieve both parent burst strength and parent tensile strength with the proper joint, of course. So it's a super repeatable, reliable, strong process. There's no particulate generated, like Jason said. Vibratory welding processes produce that like loose, flaky flash. This process does not. It's also a clean room safe welding style. And then there's no part marking. So I feel like a good representation of all these things is this glove box application. Hopefully the video is playing for you. It might be buffering or lagging a little bit, but a glove box, everyone's seen them in a car. They are very customer facing, a surface requirement. You can't have any rattle in that component, otherwise it would drive you absolutely crazy as the consumer. And we hot plate weld this style application all the time. So we're able to prevent a surface marking with tooling on the leather wrapping of the part. There's no stringing that's visible or present. I mean, even I'll play this video again. You can see when the part pulls off the hot plate, even there's no stringing between the plate and the part, which is something that's super unique to, I feel like, our servo hot plate welders, servo driven. So, and also running at that higher melt plate or heat plate temp. So I think this is a really good video that shows basically every benefit of the process all in one place.
Yep.
So were you gonna say something about?
I was just going to point out, so that part, there's a big amount of contour to that part, which means there's height on one side of the heated tool and not so much on the other side. And somebody in the audience might be going, how do you make sure the temperature is the same? And there's a couple different ways we can do that. We can either put heaters into the height, the taller portions of the tooling to make sure that there's enough heat on those surfaces. The other way is material. So a typical hot plate weld tool is made out of steel. And steel, conducts heat a certain way. There are some materials that we'll use that actually conduct heat a little bit more, like aluminum. Or we don't typically use aluminum because higher temperatures in aluminum don't go very well. But there's certain materials where we can use those for the heated tool, and those conduct the heat even faster than steel will. And so that means we'll get a more even temperature profile across that big sweeping contour.
Looks like there are quite a few questions that came in.
We'll talk about cost in a minute. We'll talk about benefits against hot gas welding. Less complicated. It's hot plate welding is less complicated. It's also a smaller machine. It doesn't need to extract nitrogen from the air.
The fact that kind of like what Jason was talking about earlier, hot plate welding naturally planes off those part inconsistencies, and non-contact welding processes do not.
Yep.
You may still be able to achieve the strength requirement you're looking for. However, planing off that part variation is quite the leg up strength-wise on this welding technology. So materials. This question has been asked quite a bit, and we get it all the time. Most thermoplastics are suitable for this joining technology. Some good examples are like your polypropylene, your ABS, your PC, your PC-ABS. I'd say those are the most common ones that we see. A lot of polyethylene as well. But all of these materials we've welded in-house with great success. And then kind of another potential variation is adding fillers into the material. The most common ones we see are glass and talc. Now we can hot plate weld materials with these fillers in. The question just starts to be how much filler will be present, because obviously if there's filler, there's less plastic. So although it might change the process a little bit, you might want to expect that with a filler, you may have to recoat the tools a little bit more frequently because glass is abrasive or a filler is abrasive. So just something to keep in the back of your mind. It's not that you can't weld with glass present, but just maybe some other considerations to keep in the forefront of your mind. Ken asked about PA6. That is a great question. We do not recommend, I was just going to do the same thing. We do not recommend nylons and PBTs. They are sticky, stringy materials that when they touch something hot, it just becomes an absolute mess. So if it comes down to that is the material you have to use, that's kind of that tipping point in when we would recommend using a non-contact heating process over hot plate welding. If it's anything in this good materials kind of category, we'd look at hot plate welding before, say, an IR or a non-contact welding method. Let's see.
I don't know what HIPS is. HIPS.
Oh, quite a few questions came in during this.
I don't know what oregano sheets are either.
I don't know what that is either. I'm very intrigued, though. Michael, I'd be curious to talk about that in depth a little bit more. Let's see, considerations related to environmental, some safety. There is off-gassing that occurs during the welding process because we're running at such a hot temp. That material is actually burning off of the plate in between cycles. So we do have a hood vent that is drawing air from the equipment to kind of vent that out.
And that typically is either hooked up to the plant's exhaust system, and then maybe it leaves the building, and other customers have an air scrubber that they might put on top of the welder. And then there's lots of customers that don't do anything because it's not harmful unless you're using there's certain materials that would be harmful. So
like a PVC.
I think most often customers are installing those types of systems because it's just a preference, like they don't like the smell or something like that.
It can get pretty stinky. I don't have any memory of doing HIPS, but absolutely happy to follow up with our applications lab on that one to see if anybody has any experience. Let's see. POM and PT are very difficult to hot air weld. How is the hot plate welding different? I'd say that the difference is the temps that we're running at allow for the material to release from the plate. POM, I do have experience welding POM hands-on, and I remember having to weld at a very, very high temp, and that kind of window to operate in was much narrower than some materials. So if you have a specific project with set specs you need to hit, I definitely recommend getting them over to us so we can evaluate in our lab. Maybe some recommendations we would have, maybe even towards a specific resin blend that we have experience with in the past, something like that might be helpful.
High impact polystyrene. Isn't that like foam?
Oh, this is interesting. Okay, I'm having a vague memory of doing some material testing come up.
Okay.
I don't recall any production equipment that has run this material, but we'd be happy to run some material testing, whether that's just coupons or a quick hand test to see how the material responds to the heat. Yeah, that would be very interesting for us to get some more information on.
Yeah, all these materials that we've listed here are, obviously like just generic material references, but we all know that there's different grades of all these different things. And whenever there's like a real specific material that you're going to be using and you really want to make sure, like that's one of the reasons why we have a lab, is that you can send us material and we can actually test it on the heated tooling and tell you like what do we find? Is it strong? Does it stick? What are the impacts of that?
And I feel like an advantage of us partnering with you through the development of your project is that we get to learn that information and know specifically how it affects your resin, because that's just knowledge that we will get to use in prototyping and then into production. Because if we're prototyping it, we know the exact recipe that needs to go into the production machine because we've done the learning already. We've already done the discovery. Yeah. So it's a huge advantage for us and gives you the warm fuzzies. One person asked if you can mix materials. Yes, if they are compatible. I'd say that's my answer, but we'll see like a lot of copolymer materials, a lot of copolymer polypropylene right now is super common. So we haven't talked a whole lot about coatings, but the most common ones that we use are Teflon and chromium. I'd say that this covers 97% of the welding applications.
Yes. Oh, yeah.
Teflon is becoming a little bit more of a tricky coating to use, as there's some European regulations, from my understanding, that are starting to push away from Teflon. Yep. So we've had to do a little bit more testing with temperatures with the chromium or other style coatings. So if you can't use Teflon, we're happy to try and figure something out. It's a bit longer of a cycle, but like Jason mentioned earlier, we have seen some customers prefer to use Teflon so that they can run at those lower temperatures because they believe that it gives better long-term strength of the part.
Something I want to point out, so this video shows for the Teflon side that there's a sheet on there, like a replaceable sheet. That is one way to do it if you have a flat weld. More often than not, we actually have the tool, the steel is actually coated in a Teflon. And the big difference in that video that you noticed, that one cycle time was a lot longer than the other one, and that's temperature driven. There's a lot less energy to start with, so it takes longer for that to get into the plastic.
Yeah, if you run Teflon at higher than 500 degrees, you're starting to degrade that Teflon.
Yep. So a couple questions. Is there a max surface area that can be welded, such as 2 large thick rings? Practically, you can go very, very large. We've welded pallets, very big pallets, and we'll kind of show some of that in a minute or two. There's really not a limit, I would say, to this amount of surface. It's a matter of whether you can build a machine that can hold that part and apply enough force to the weld surface evenly. And if you can accomplish all of that, you should be able to hot plate weld it.
I always like to tell people that with custom automation, the sky is the limit. But whether or not you like the price tag associated with it is the next hurdle.
Yes, there's that too. There's, the bigger things get, the more expensive they get.
Typically, how is weld durability characterized? I understand that depends on part geometry, checking if there are any standards or recommendations from Extol.
Is that question about like how well is the part welded? Because we can do leak testing, we can do burst testing. Those are common things for something that has a hermetic seal. We'll do tensile testing, where you're actually just pulling your weld joint apart, whether you're taking a section of the weld and pulling that, or taking the entire assembly and pulling it apart. We've done peel testing, where you're trying to torque it sideways and see if it'll break off. We can do shear testing. There's lots of different ways. So those are the 2 main things, though. Does it leak and is it strong? And those are some of the tests that we commonly see. Other tests that I know some of our customers do, we don't have the ability to do a creep test in our lab, but that's something that people will do especially for a degas bottle, which is the application on the screen here. Those have to be able to withstand higher temperatures for long periods of time. These are living inside of vehicles, and they better last the life of the vehicle. And so there's tests that customers can do where it's a long-term elevated temperature, and they're pressurizing the part for a long period of time. That's a test that some people do. Shaking, like a vibratory test, to see what happens if you shake the crap out of this thing for several hours. I don't know. So there's lots of different tests that people are doing. So we're going to get into the applications now, some different examples. And these are just examples, things that we see commonly. We've seen a whole lot more than just the 5 examples that we're going to show you today. One of them is in engine degas bottles. These have internal walls that are being welded, and this part is pretty stout. These need to be very strong. But because of the geometry of it and the material that's used to make it, there's big amounts of sink that show up on the weld surface. Again, this is an area where if you're not hot plate welding this, it would be difficult to get a good consistent strength and good consistent leak proofness, because there's all this, the weld surface is supposed to be flat, and there's big areas where it dips way down because the part has shrunk after molding, and in some of the thicker areas it shrinks more than others. And so because we're planing that off and making sure it's totally flat before we weld them together, we get good strength with hot plate welding. It's a high pressure application. This is one where we almost always are doing a burst test. And when we burst test these, the part cracks and breaks open, but not at the weld. The weld itself achieves a better than parent material strength because the weld rib is made to be wider, slightly wider than the actual wall thickness of the rest of the assembly. There's no particulate. These have to be clean, and there's a hermetic seal. So in general, this is an example of a polypropylene part that lives underneath the hood of an engine. There's lots of other polypropylene and other plastic materials inside of an engine of a car, and a lot of them are hot plate welded. So.
Another application is automotive glove box. We watched a video of this already. Like Jason mentioned earlier, that big contour to the part also makes it difficult to join any other way to get that even heat all the way across that contour. So the big things are no part marking. You get a strong weld. You're not having any buzz, squeak, rattle present when you're driving down the car and your glove box is that would drive me bonkers. Just thinking about it makes my blood pressure spike a little bit.
Yeah.
And then you are able to hide the weld with that leather wrapping. It kind of acts as its own kind of skirt present. There are some considerations to have for that leather wrapping. It can't overlap with the weld rib. It can't, have too much overhang. The glue spraying across the part to put the wrapping on should be taken into consideration when welding is being set up. But a lot of other automotive trim components are great for hot plate welding. We've done center consoles, which there's a video of that later, smaller trim pieces. Automotive in general, the materials that are used are just great potential opportunities for hot plate welding.
Batteries. This is an example of a automotive battery, but we can also do batteries for energy storage. So maybe a larger scale. We've done batteries for more industrial type applications. So much bigger than what you see on the screen here. Batteries are very commonly hot plate welded, and we've done several of them. And there's something to point out here is inside of a battery, there's stuff, right? I don't know exactly what's in there, but they're heavy because there's all kinds of metal things and fluid and acid and whatever. Like hot plate welding is a process that can deal with that. Like it's okay because you fill the battery and then you weld this lid on. And that can often be automated, whether you're having a robot feed it or maybe parts are coming in and going through the side of a hot plate welder. You get strong, robust welds. You need it to be hermetically sealed. There's sensitive components inside of the battery, and those are kept safe from the hot plate process. And there's no particulate. So energy storage and battery applications are great for hot plate welding.
Another kind of industry that is a really big hit with hot plate is medical. Because this is a particulate-free process, the equipment can be run in a clean room. It does have a special package that's applied to it to make it clean room safe, but it can be put in a clean room. Makes it super flexible for medical. That hermetic seal is often critical for a lot of devices that we see. So overall, there's just hot plate welding naturally is very well suited for medical with very little extra considerations required.
Pharmaceutical filtration. So the first line there, stack weld. That is the component that you see there is actually welded 1, 2, 3, 4 times, and there's multiple layers. And the way that you can do that is you stack parts on top of each other. So you do the first weld, and then you add the next layer, weld it, add the next layer, weld it. And we've done some for pharmaceuticals. Other industries are utilizing this as well. If you have a consistent weld plane and you need to stack multiple layers on top of each other, that's something that hot plate welding can do, and particularly servo-driven hot plate welding. You need that welder to adjust its parameters between every single layer because the part is getting taller on one side while it's staying shorter on the other side. So in pharmaceutical filtration, we are able to do stack welding. Again, hermetic sealed, no particulate. It's clean room certified, so you're able to get good parts out of it, and you don't have to worry that you're going to have to clean the parts afterwards.
Got a question. What are the limits of hot plate or hot plastic welding? Which temperatures are recommended? Closed to melting temp. So it's a bit of a tough question because it's very dependent on what material you're welding. PCs, you're going to want to weld at a higher temperature to burn off any potential material stringing. Polypro can be welded at a much larger range. HDP or the polyethylenes need a Teflon coating, so those are going to be welded at like 450 degrees. So I'd say that at its base model, the rapid conductor can weld anywhere from 400 to 900 degrees. If we need to reach higher temps, we can use higher rated auxiliary heaters. However, anything over 900 degrees is typically going to a non-contact process, and that's why you need that extra heat. So hopefully that answers your question.
And of course, we can look at any specific applications afterwards too.
And provide maybe a little bit tighter of a range of what that temperature may be. So you may be thinking, this is really great information. Now, how do I design my part for hot plate welding? Because I am sold. Well, if you click on this link or visit our website, you can see our hot plate welding design guidelines. They are a great resource to get started. However, Jason just put them in the chat. Thank you so much.
And you actually can click the link on the PowerPoint. I tested it.
Did you click it to put the link in the chat? Amazing. They are a great starting point for you to design your part for hot plate welding. But don't worry, you do not have to do it alone. Please send your CAD to our applications lab. They will review it with a fine-tooth comb and tell you this area needs to be changed, add more retention features here, all that good sort of stuff. A couple things you will see on the design guidelines are just the recommended sacrificial material. Remember, we talked about that material is displaced as flash. So we have minimum recommendations for what that material overlap should look like for most processes. I'd say I haven't seen anything lower than what's on the design guidelines. However, if you wanted to put more material overlap in, or you wanted your weld rib to be 7 millimeters wide for some reason, it's possible. We can make it work. You just might have a lot of flash. So don't see this as the end all be all hard rule. Let's have a conversation about what you need to achieve. And then weld contours. This was also a question I think came up in the registration. What does it look like to weld something that maybe has multiple planes? We recommend 30 degrees is the minimum weld contour. The maximum. Add anything over 30 degrees. We want to see only 90 degrees. Just kidding. Please don't do that. 30 degrees is the maximum. I almost did it again. The maximum angle we want to see in the part geometry. The reason for this is when the parts come to seal together, that angle starts to act as kind of a slide. And so you're smudging that molten material past itself, not necessarily getting a good force into that angle. So that's kind of the reason why 30 degrees is our recommended angle maximum. We have done a little bit more than that. So if you have an application where you just can't get to 30 degrees, let's test it. Let's see if we can hit your specs. We have a question. Is any fixture cleaning required after hot plate welding? Polypro 30% glass filled.
TDC,
Yeah.
I think we would do that, and no.
Yeah. Do a chromium finish on the hot tools, and then I don't think I've seen any cleaning required typically.
Would we weld that at 800 degrees?
Probably something pretty high. Yeah.
Okay.
And then weld clearance. So say you've got that internal component like a battery, or you have a skirt on the exterior to prevent that ugly flash from showing. That's totally doable. You just need to have clearance for your heated tool. So your heated tool needs to have about 1.52 millimeters of clearance from those features. Again, this is a minimum. You can add all the space you want in between as long as you have more than 1.52 millimeters of clearance between those components. If you have something that you want shielded from the heat, insulated from the heat, a little bit more might be required to get that insulation in.
Max temperature for Teflon coated tool.
I think we say typically we don't want to run higher than 450, but I believe Teflon can technically go up to 500.
Yeah, I think I've run 500 quite a bit. I was going to say like 550, wouldn't want to go above. Yep. And then anything beyond 550, you get 600 and that Teflon is going to start to degrade and wear out really fast. Yeah, you can probably run a little bit on that warmer side with a Teflon sheet versus a Teflon coated tool. You'd probably want to stay a bit colder. Otherwise, you'll be recoating, I don't know, every 10 cycles, 100. Regardless, it will not be fun. Yeah. Best hot plate material for Polypro glass filled 20%. That's a good question. Anything that's got a filler in it, you do not want to use Teflon, so we would go straight to chromium. Yep. Weld surface angles. Similar to that weld contour of 30 degrees, you want your weld surfaces to be parallel to each other because of that force of sealing, the direction that the force is sealing in. So we do not like to see this condition. What happens is you'll displace all the material on this right side. So you're touching cold material and cold material, which is bad. And then you'll maybe just barely have some soft material touching on the left side here, which is also bad. So it does not produce a strong weld, is not recommended. You can have the weld plane be parallel to each other and the parts be at a slight angle. It's not great, but depending on your spec, might be doable. The best case scenario is having the weld plane perpendicular to the actual direction. The weld plane be perpendicular to the wall stock. If the temperature exceeds 550 degrees, do you recommend chromium? What other options? I say yes, if you need to run at those higher plate temps, then you would not want to use Teflon. And as far as disadvantages, different materials respond differently to using higher temperatures or lower temperatures and different nonstick coatings. And so there are certain instances where a material might not stick to Teflon, but it will stick to the chromium coating. So there's, lots of development that we've done over the years to try to find the best coatings for the best materials. And those are the two that we most commonly use. You mentioned a temp up to 800. This is far away from typical melting temperature plastics. Yes, it heats it quickly. What is with the flash? This flash will be thermal degradation. The flash, when we're using those higher temperatures, we're not melting for very long. And we'll see that in a video here in just a minute. There might be small amounts of degradation, but it's very uncommon for us to see any kind of material that's like falling off of a weld. Like that would be very rare. So there's two types of machines shown up here. One is servo driven, the other one is not. So two types of motion control that are common for hot plate welding equipment. Pneumatic. Those are typically less expensive. So you can, in the way to control the positions, you use hard stops. You use mechanical features in the tooling that will contact each other to make sure it doesn't go too deep. And you use electronic pressure regulators to help try to regulate the amount of force that you're applying to your parts. It's good for simple, smaller welds, and maybe welding multiple components on one part. We'll see an example of that. And then servo, which is becoming more and more common. Extol was one of the first, maybe the first, to introduce servo-driven hot plate welding to the market. You don't have any hard stops, so you know all of the force that you're applying goes into the part. It's precise control. It's very fast. It's good for complex welds like the glove box that you saw. It's good for large welds and for stack welding. So here's the rapid conductor. It's a machine that we've been building for many years. Some of the benefits are interchangeable tooling, and you can weld multiple different products through the same machine. Compact Fusion is a much smaller but still servo-driven platform. Same thing here. You can do quick tool changes and allow yourself to run multiple product variants through the same machine.
Dennis had a question of what's the smallest footprint of one of your machines, and I feel like that's the answer.
I think the Compact Fusion is probably one of the smallest ones, and this thing is 2 feet by 3 feet.
That's exactly what I was going to say.
So it's not a very big machine.
We've got some questions about what coating is best for polypro copolymers. We've welded copolymers with both chromium and Teflon. So really it came down to part geometry and how the part was stressed under like the burst test or leak test and needing to get maybe a little bit of strength out of it. So we have definitely tried both, depends on the application. And then we've also got a question that is, what is the best or maximum dwell time to maintain between melt and weld?
That is very application dependent. So, I mean, dwell times can range between 1 second and 60 seconds.
I'm wondering if this is like open time.
Oh.
Is the best or maximum
between melt
and weld.
Okay, so now you're getting to something that's very important. So the open time, after you've melted your parts, you've put a bunch of heat into them. As soon as you come off of that heated tool, they're cooling off. And we want to make sure that we get those parts back together so that they can weld before we lose too much heat. If you start to lose too much heat, that top surface can get skinned over. You get a cold weld when that happens, and that results in leaks and poor strength. So typically you want a quick open time, as fast as your machine can go for the open time. And we'll see some more examples so you can get an idea about just how long that is. This machine that's shown on the screen here is one of the machines we built to weld pallets. So think parts that are 4 feet by 6 feet, large parts. Here's an example of a hot plate welder that has some automation involved with it. There's a conveyor that's bringing in the lower half in from the side, and then the upper is fed by a robot arm that's picking from a stack of parts. So the upper robot arm grabs that upper component and loads the upper tool. And then the lower component is coming in on a conveyor, and then the machine locates everything to make sure that we're supporting the parts correctly. Do you have any recommendations for troubleshooting weld failures? That might be the topic for discussion beyond what we can cover here in this webinar, but we can certainly follow up with you specifically to go through that.
And then Alan asked a question about, does Extol have a hybrid technology using IR and hot plate to speed up, kind of like an IR preheat is what I interpret that as.
I don't think that would actually speed it up, because IR heating is going to be slower than hot plate heating, and because conduction is, in this case, probably the fastest way to heat up plastic parts. So we don't have anything like that. You know, you see that kind of a hybrid technology with vibration welding. And the purpose of that, it doesn't speed the cycle time up, it actually slows it down. But you do an IR preheat on vibration welding to reduce the amount of particulate that's generated from the vibration and the friction. In this machine example, this is a center console. And so it's a big part, and it's got lots of contour. It's decorative. People are going to see it. Here the operator is loading the sides, and this machine was actually capable of doing a tool change between two different variants. So the two side pieces are rotating because it recognized that it was switching part variants. And then they come in and grab those decorative trims off of the main center console. And then the heat plates come in. There's two of them. And we're going to do two hot plate welds at the exact same time. This is a pretty big machine as well, because there's lots going on. custom machine. So that's why, you can do a lot when you have a custom machine. You can accommodate a lot of different applications. This is the big pallet weld machine that we were referencing earlier. This is showing a dry cycle. And so you can kind of see how it moves around as the video kind of pans around the machine. You can kind of see what's happening on the inside. This particular pallet was designed with segmented welds. So there's 9 weld pads, and you can see those little green things. Those are the actual heated tools that are contacting the plastic. I'm going to probably skip past this. So this is an example of a pneumatic welder. And so here you've got 2 parts that are going to be welded. They are doing a pneumatic weld. So we're welding a small component onto a larger part. Mm-hmm. So here the heated tool is pushing onto the plastic, and then there's this small component being welded onto it. And you can picture these kind of hot plate welding modules being able to come at many different angles to weld onto this part. So lots of different customized equipment can be done. Large pallet welds, modular pneumatic welds, robot fed welders, independent 2-up welders where you got welders maybe sitting side by side and they're both welding the same part, and then conveyors are feeding them independently. Multi-stack welders, 6-up welders on a rotary dial. We've done that before. 2-up collaborative welders, and just the possibilities are pretty much endless.
Custom automation, the sky's the limit.
There it is. Yeah. So I think there's 4 things that we hope you kind of take away from this. Is in hot plate welding, you get strong welds that are leak proof, and they're clean and they're safe to use. So that's what we're hoping that you remember about hot plate welding. It's actually the process. I think sometimes gets a bad name from some applications. Poor equipment, maybe. We hear people complain about, there's sticking on the hot plate, and I think with the right machines, an Extol machine, we typically don't see that because we're doing the applications work up front to make sure we're not getting you into a bad scenario by saying, yeah, this will work, and then it doesn't work. So we'll test things and make sure that it's going to work. And then our machines are very, very capable. So with hot plate, to avoid sticking, you really want to make sure you have good control of your process, and you need a good machine in order to do that. Mm-hmm. Questions. Can we use tubular flexible heaters in hot plate instead of cartridge heaters? I suppose you could.
Yeah, I don't see why not. I don't think that we've had a situation where we've needed to explore that yet.
Yeah. As long as the heater is robust and it's not going to burn out on you, and it's able to generate enough heat to heat up the whole tool, then you're good to go. We're kind of at the end of our time here, so and you can keep asking questions. You're more than welcome to do that. I have a question for you. Would you like us to train your team? So I mentioned it at the beginning. We welcome the opportunity to come into your facility and provide training to your team. If you think that this would be beneficial for them, we can talk about hot plate welding. We can also talk about other plastic joining technologies or do a whole overview of them. We do this regularly with lots of different customers. We come in, sometimes we'll bring in lunch if that's something that you're into, and we present the technology. We make it very interactive. We answer your questions. And if that's something that you think would be something that you guys would benefit from, let us know in the chat or send us an email afterwards. Tell us, say, yes, I'm interested in training. And then we can follow up with you afterwards and make sure that we can schedule something and get you guys in. Here's our contact information. If you want us to talk about a specific application or get started, there's our 2 email addresses. Send us an email and we can start you through the process. We'll look at what you've got. We'll give you recommendations. We'll get you hooked up with our team. If you need to talk to a salesperson, we can get you in contact with a salesperson. If you need to troubleshoot a machine that you already have on your floor, we can get you in discussions with an engineer. Just send us an email and we'll get you the help you need. Thanks everybody for joining. I hope you guys have a great rest of your day.
And a happy Halloween.
Oh, and
I had to throw it in there.